So good day everyone, I'm here in front of you to discuss about inductors. So first of all, what is an inductor? An inductor, also called as coil, choke or reactor, is a passive two-terminal electrical component that stores electrical energy in a magnetic field when electric current flows through it. So basically, in a circuit, when an electrical energy passes through a magnetic or in an inductor, so it transforms the electrical energy into a magnetic field. So when it passes through, electrical energy, kanang inductor stores electrical energy and kanang transforms into a magnetic field. So if the current changes, so does the magnetic field. So when there is a bigger current, there's also a larger magnetic field around the inductors. So it temporarily stores energy in a form of magnetic field. Concept of inductance. Inductance is the property of an electric conductor or circuit that causes an electromotive force to be generated by a change in the current flowing or the inductance of the winding. So inductance is directly proportional to the number of turns in the coil. So the greater number of the turns of the coil, the greater its inductance of the inductor. Inductance also depends on the radius of the coil and on type of material around which the coil is wound. So inductance will also depend on how long its radius and what type of material will you use on the circuit. So the purpose of inductor is to oppose any change in the magnitude of current within a circuit. When you have a current flowing through a wire, you'll create a small magnetic field around it. So if you coil up a lot of wire, then you'll get a stronger magnetic field. So basically, it illustrates like this. So when you have a current flowing through a wire, you'll create a small magnetic field. But if you coil a lot of wire in a circuit, so you'll produce more magnetic field compared to only current flowing through a wire. When current starts to flow through the coil, a magnetic field starts to expand. It then stabilizes, and then you will get some energy stored in the magnetic field when it reaches maximum current of the circuit. So when current starts to flow in the wire, you'll create a magnetic field starts to expand. So when current starts to enter the inductor, a magnetic field starts to expand. Then it will stabilize when it reaches its maximum current in the circuit, towards the circuit. So basically, like if the maximum if the current of the circuit is 2 ampere, so the magnetic field will stop at basically 2 ampere or 1.99 amperes, something just like that. Then when you turn off the circuit, so it will not turn off immediately. The magnetic field of the inductor will slowly, when the current stops flowing, the magnetic field starts to collapse, and then the magnetic energy gets turned back into electrical energy. So they are like temporary storage area for energy. So if the current stops flowing, the magnetic field starts to collapse. So it will slowly fades, and the magnetic field or the magnetic energy will transform again into electrical energy. When magnetic fields are created, inductors prevent instantaneous changes in current in a circuit.
Now we will discuss about the inductors in series and parallel. So inductor is represented by the symbol like this, and stated by the symbol L, and the SI unit for inductors is Henry or Henry's or H. So voltage is time varying in the inductors, and also current is time varying. So the voltage across the inductor is directly proportional to the rate of change of current in the circuit. So voltage across the inductor is directly proportional to the rate of change of current in the circuit. So that L, or the symbol of inductor, times D, I, T, over dt. So, where L is the proportionality constant. So L there is the constant. So if we are now able to know the voltage across the inductor. So to simplify further, so if we want to get the current, so current equals 1 over L times the integral of V dt. The limits negative infinity t. So in inductors, in answering inductors in series of parallel, we need to focus on this two. Inductors in series. So we can say that this is a series circuit. So we know that the total voltage in a series circuit is equal to the voltage in L1 and voltage in L2. So we can simply say that VL, so total voltage is equal to V1 plus V2. So by further substituting the voltage in the inductor, so V of T is equal to L times VIT over dt. So we can say that substituting V1 and V2 will become to this V1 is equal to L1 times D I over dt plus V2 L2 VI over dt. So also for the total voltage, so total voltage will become L equivalent of V I dt. So we can say that we can cancel this. We can get L equivalent as L1 plus L2. So if we have if there is more, so we have now the equation L equivalent equals L1 plus L2. If there are more inductors in the circuit, if it is in a series, we can still continue this L. So this is now the formula of inductors in series. So now we will go to inductors in parallel. So we can see there is a circuit that is. Now we will go to inductors in parallel. So we can see here that there is a parallel inductors in a circuit. So we know that in parallel circuit, the total current in the circuit will be equal to the current in this area and current in this area. So we can say that total current is equal to I1 plus I2. So to further substitute, we know that the formula in current in inductor is this. So to substitute, I total here will be I equivalent. So it's 1 over L equivalent times integral of dt. The limits negative infinity is equals to I1. So I1 will be 1 over L1 times the integral of V1 dt times the limits negative infinity Look at the ordering. Plus 1 over L2 times integral of V to dt the difference negative infinity. So here we can cancel out these 3. So now we will get 1 over L equivalent equals to 1 over L1 plus 1 over L2. So now we have the equation for inductors in parallel.
Answer this example in inductors and series and parallel. So, in this example, we need to find the L equivalent in the circuit. So, in finding the L equivalent, we can just use network reduction in this kind of example. So, we can just combine these two parallels like this. So, first, let's put here L1, L2, L2, L3, L4, L5, and L6. So, first we need to combine the L1 and L2. So, L1, 2 is equals to 10 times 10 over 10 plus 10 equals, and also here in L3 and 4, L3 is equals to 15 times 5 over 15 plus 5. L3 and 4. So L3 and 4 is equals to 3 and 4. Stop sabi. So the answer here is 5 henries. And in L3 and 4 is 3.75 henries. So we'll get now, we will have now a new circuit like this. So, so now with the new value of 5 henries, 3.75 henries, and L5, which is 30 henries, and the L6, which is 20 henries. So now we can easily add up this because this is series. So L5 and L3, 4, 5 is equals to 3.75 Henry plus 30 Henry equals to 33.75 Henry. So, and after that, we will come up a new circuit like L equivalent of 20 Henry, 5 Henry, and 33.75 Henry. So now we can use the parallel. So like this, we can easily L of 3, 4, 5, 6. This is L6. So L3, 4, 5. So 6 is equals to 20 times 33 0.75 all over 20 plus 33.75. So the answer will be 12.56 Henry. So finally, the last circuit, you can all know the circuit is now reduced. So like this. So 5 Henry plus 12.56. So now we can get the L equivalent of the circuit. Like L equivalent is equals to 5 Henry plus 12.56 Henry will be equal to 17.56 Henry.
Discuss about the inductive reactance. So inductive reactance is the name given to the opposition to a changing current flow. This impedance is measured in ohms, just like the resistance. So we have here the formula of the inductive reactance, which is X of L is equals to 2 pi FL, where X of L is the inductive reactance measured in ohms, the F, the frequency of the electrical supply, which is in hertz, and L, the inductance of the coil, or the inductor, which is in Henry. So we know that the inductive reactance or the impedance is measured in ohms. So we can just substitute the formula by this. X of L is equals to VL, V sub L over I sub L, where X sub L is the inductive reactance, the impedance, V, the voltage in the circuit, and I, the current in the circuit.
So now let's answer this example of an inductive reactant. So the example is, a coil with an inductance of 0.3 Henry is connected to a 120 volt 60 Hz AC circuit. So calculate the inductive reactance and the current of the circuit. So first, we need to get the diagram. So 120 volts and 60 Hertz and 0.3 Henry. So solution. So from the equation of X sub L, or the inductive reactance, is equals to 2 pi FL. So equals to 2 pi times the frequency, which is 60 Hertz, times the inductance, which is 0.3 Henry. So you can now have the answer of 113.1 ohms. So we now have the inductive reactance. So in finding the current, so X of L is equals to V over I. So pause ko rin. Go. We simply transpose it. So V is equal over I is equals to V over the inductive reactance. So which is the voltage is equals to 120 volts all over the inductive reactance, which is 113.1 ohms. So the answer now will be 1.06 amps. So that's all. Thank you.